Okay, so in this video, guys, what we're going to do is have a look at how do we calculate the pH of a resulting solution from the mixing of and reacting of an acid, a strong acid, with a strong alkali. Okay, now this is not to be confused with the next video, which will allow us to work out the pH of a buffer made by mixing an excess weak acid, with a strong alkali. Okay, and it's really important that when you read the question in your exam paper, that you make sure that you don't get these mixed up. Students get them mixed up all the time. So this is like if you did a titration, okay, between a strong acid and a strong alkali, working out the resulting pH of that. Okay, now there will be clues in the question whenever you're doing it as to what type of question it is. This will help you understand how to work out the pH of a buffer that's made with an excess weak acid and a strong alkali, which will be the next video in this series of videos. Okay, so let's have a look. As you can see from the title, it's talking about calculating the pH of a mixture between an acid and an alkali. So we'll start off really simply. We should have all the tools required in order to do this already anyway, so it's just applying those bits of information that we have already got our hands on. Okay, so let's have a look at the first one I've chosen a couple to begin with, which are really very, very simple. Okay, just to get the concept across to you, and then as we go through, they're a little bit more difficult. There's plenty of these in your question books as well, which you can have a go at. Right, so let's have a look at the first one. We have taken a mixture of hydrochloric acid and sodium hydroxide. You can see the equation, hydrochloric acid and sodium hydroxide. So the first thing we need to check here is the acid and the alkali are both both produce 1 mole of hydroxide ions and 1 mole of hydrogen ions per mole of the sodium hydroxide or the hydrochloric acid. So what have we got? We've got a volume, I said, of 25 cc's of the acid, 50 cc's of the sodium hydroxide. The acid is 0.2 mole per dm cubed and the alkali is 0.1 mole per dm cubed. What we would do there is we would take our number of moles equals concentration times volume and do that for both. So in terms of the number of moles, then N of both of them, it's exactly the same. Okay, now what we remember in a neutralization reaction is that a neutralization reaction is H plus ions plus OH minus ions to give me water. And if we look here, the number of moles of acid and the number of moles of alkali are the same, which means because they produce 1 H plus and 1 OH minus per mole of acid and alkali, the number of moles of H plus and the number of moles of OH minus are also the same. Now, if the number of moles of OH minus and H plus are the same, you get a pH of 7. Very simple. Okay, so there you go. Nice, simplest one you can get to get you going. Okay, let's have a look at the second problem. Second problem, very similar. You've been told about the concentration and the volume of both the acid and the alkali, but this time, okay, we need to be careful because my acid is a diprotic acid, so every mole of it gives me 2 moles of H plus ions. Okay, my alkali, every mole of it will give me 1 mole of hydroxide ions. And again, I remind myself that neutralization is 1:1 H plus OH minus ions. Okay, now the reason why I do it like this is to avoid taking into account the 1:2 ratio here. Okay, there's other ways to do this which take those into account. I find them a bit more complicated for students, so I go via the route where I get each time to number of hydrogen ions, number of hydroxide ions, and then I know that they react in a 1:1 ratio and I can go from there. Okay, anyway, let's have a look. So my moles of my acid is 0.0125. Again, I just do N equals concentration times volume over 1,000. And my moles of my potassium hydroxide is 0.025. But remember, I always want to get to moles of H plus ions and OH minus ions. Because every mole of the acid gives me 2 moles of H plus ions. I get moles of acid, I multiply it by 2, give me 0.025 moles of H plus ions. Remember, every mole of my potassium hydroxide, which is this value here, gives me 1 mole of hydroxide ions. Okay, that means that if I have that number of moles of potassium hydroxide, that's how many moles of hydroxide ions I have. Again, if you look, moles of hydroxide ions equals moles of hydrogen ions in this context as well. They are in a 1-to-1 ratio. If they equal each other, pH is 7. Dead easy. So there's the first two. I'm trying to get through the principle of working out the moles of H plus ions and the moles of OH minus ions. Okay, right, let's move into a third example here. So if we look at this one, again we've taken a nice simple HCl, remind myself, HCl is monoproduct, 1 mole of it gives me 1 mole of H plus ions, and potassium hydroxide, 1 mole of it gives me 1 mole of OH minus ions, and just remember that H plus OH minus ions react in a 1-to-1 ratio in a neutralization reaction. So there's my concentration and my volume of both of those. Again, I just do N equals C times V over 1000, and there we go. There's your moles of acid, there's your moles of alkali. I multiply both of them by 1, or just keep it as it is, because each of them provide 1 mole of H plus or OH minus ions, but this time the moles are not equal. Okay, so I have my acid, or in other words my H plus ions, in excess. Okay, and I have them in excess by a factor of 0.0125 minus my moles of alkali, or OH minus ions moles, yeah. Okay, which means that's how many moles of hydrogen ions, 0.0045 hydrogen ions, I have in excess that are left over at the end of the reaction in the beaker or the conical flask unreacted. Now remember, to get pH, I've got to get H plus ions concentration, not just number of moles. So therefore, I take my number of moles, divide it by the volume this time, so there's my moles, divided by the volume of 0.09. Remember, these number of moles of H plus ions are now in a combined mixture of 90 cubic centimeters, or 0.09 of a decimeter cube. So that's where the 0.09 or the 90 cc's came from. This gives me concentration of H plus ions. I minus log that, and this time I don't have a pH of 7 anymore. I'm not doing those simple little ones anymore, and I have a pH of 1.3, and that's what I'd expect. If I have a strong acid in excess, you're going to expect a pH of around sort of between 0 and 2. If you got a pH sort of if above 7, you definitely would redo that calculation, because there's no way that that's possible. You made a mistake somewhere. Okay, let's move on to the next one. Same question again, okay, except this time we have concentration and volume. Again, moles, remember, KOH gives me 1 OH minus, HCl gives me 1 H plus per mole of that. So there's my moles of potassium hydroxide. That's my moles of acid. I want to get to moles of H plus ions and moles of OH minus ions, so I multiply those by 1, of course. Of course, give me the same value. I can see this time that my hydroxide ions are in excess, yeah? They're in excess by a factor of 0.35 minus the moles of acid that will react with, so this minus that, okay, gives me 0.2 moles of hydroxide ions left over. Remember, I've got to convert that, however, into concentration, so C equals N divided by the V. The volume is, I've got 500 and 300, so it's 800 over 1000, so it's 0.8. So my concentration this time, and it's of hydroxide ions this time, is 0.25. Now this is where there's an additional step when you have the alkali in excess. We got to go back this time to Kw, and remember H plus ions, when we have an excess of alkali, is Kw over the concentration of the OH minus ions, which we've already worked out at 0.25, gives me my H plus ion concentration, comes out at 4 times 10 to the minus 4, minus log that, gives me 13.4 pH. That's what I would expect. I've got a strong alkali here in excess. I'm looking for an answer in around sort of 12 to 14. If I didn't get that, I'm probably going back to my calculation to have a rethink. Okay, right. So this time, same sort of principle as one, I think it was the second example that I did. Okay, so just remember, I've got sulfuric acid is diproduct. So every mole of that will give me 2 H pluses, whereas every mole of sodium hydroxide will give me 1 mole of hydroxidants. So again, there's my concentration of each, my volume of each. I do my N equals C times V calculation from here. Moles of that, acid is that, moles of alkali is that. Reminding myself that I always want to get to H plus and no H minus ions. So I multiply that by 2, okay, gives me 0.25 moles of hydrogen ions here, and I multiply this by 1, gives me 0.08 moles of hydroxide ions there. Clearly the H plus ions are in excess, and they're in excess by about 0.25 minus 0.08, which is 0.017. My volume this time is 450 cubic centimeters, or 0.45 decimeters cubed. So that's my concentration of H plus ions here. That's simple, all I do is minus log that, and again I have a strong acid in excess. I expect a pH between sort of 0 and 2 probably. Okay. Right, I think this is the last example that I'm going to do here. There's lots of these, as I said, in your notes. Okay, so let's have a look. We have nitric acid, which is monoproduct. So the moles of nitric acid will equal the moles of hydrogen ions. Barium hydroxide, however, the moles of barium hydroxide will only be half the moles of hydroxide ions, so I need to double them. Concentration of each is given by the examiner at 0.4 and 0.5. The volumes are both at 50 cc's. So the moles of acid is 0.025, the moles of alkali 0.02, the moles of hydrogen ions therefore is that times 1, gives me that's my moles of hydrogen ions. But remember, my moles of hydroxide ions are that times 2. Okay, so that's my 0.04 moles of hydroxide ions. Clearly my hydroxide ions are in excess, and we know that in neutralization they react in a 1-to-1 ratio, so the bigger number at this point is in excess. They're in excess by a value of 0.04, that's my hydroxide ions, minus my hydrogen ions because they react in a 1-to-1 ratio. So there you go, there's your moles of hydroxide ions that you have left over in excess. But remember, we have to get those into concentration, so we do C equals N divided by V. The V is 50 and 50, which is of course 100 cc's, or 0.1 dm cubed. Okay, so we divide the moles by the volume. The concentration of hydroxide ions is 0.15 in this instance. Remember, when hydroxide ions are in excess, we go to our Kw. Kw equals OH minus ions concentration. Okay, which is 0.15, gives us H plus ion concentration. And we, of course, to get pH, we minus the log of the H plus ion concentration, and again we get 13.2 in this instance. We have a strong alkali here, it's in excess, and again that's a value that I would probably accept quite readily in an exam. If I was you, put it down, that looks like a right answer. Okay, if you got anything sort of outside that 12 to 14 bracket, you might start maybe going back if you've got time and checking your answers. Okay, hopefully that allows you to get a good idea of what you do when you have got a strong acid reacting with a strong alkali, and you've got to work out the pH of the resulting solution. Okay, and this will help you in the next video whenever we're talking about working out the pH of a buffer made between an excess weak acid and a strong alkali. There's lots of these questions, by the way, very similar to this in your class notes and in your calculations textbook. So I suggest you go and have a go at a few.